Good afternoon. My name is Luis Armando Perez Rey, and I will be presenting the final presentation of the seminar on data mining from the Eindhoven University of Technology. First, I will just be projecting the presentation, and then I will be starting everything. Sorry? Yes. So my name is Luis Armando Perez Rey, and I will be presenting the project on learning to orient with video pixels, with supervisors Vlado Minkowski and Jim Porteous. This presentation is divided into first a recap on the topics already talked about in the first presentation. The second part is the analysis of the dimensionality reduction techniques I will be talking about. The third part is the results obtained, and finally, the conclusions. So recall, what is the main research question of this project? It is whether can we learn the notion of orientation from video recordings. Basic setting of this project is that we will be having a small robot that will be taking video images from its surroundings. Each of these images is produced at a certain position. Each position will be storing value of what's the true orientation of the robot. Since the data is inherently high dimensional because it's video images, we will be trying to attempt a dimensionality reduction that will still be capturing interesting properties of the data. From this dimensionality reduction, we'll try to approximate to the real location and orientation from which each of the images was taken. In the previous presentation, we defined the following workflow. The first part corresponds to the dimensionality reduction. We'll be testing how good can the data be embedded into smaller dimensional space. The second part is to test the generated embeddings and whether they can really allow to reconstruct the positions at which each image is taken. The third part is to extend to non-stationary room. That means that we can just change the room or just place the robot in a new room, and it will be able to also orient itself. And finally, the fourth part is to use the model for certain tasks that require certain knowledge of the orientation in space. In the previous presentation, we talked about this article in which it talked about an artificial video game player that could already represent the images that it was seeing into a lower dimensional space. And the interesting part is that similar images are just mapped together. In the end, our project is aiming at something that is very similar. If we take images from positions that are quite close, like for example, these images from the library at TUI, both of them should be really close because they were taken from positions which were very close. So in the first part, we'll be focusing on the dimensionality reduction and why it is so important. Well, not in the first part, but in this part of the seminar, we focus on the dimensionality reduction and which would be the appropriate choices of the best method to do so. I will be now describing some of the methods that were investigated and then talked about what was the decision of which is the best model to be used. The first method is diffusion maps, and it's based on the idea that we can construct a graph over the data points that we have. There are going to be some edges, and these edges will have a weight with a value that is proportional to how close they are. Two values are close, they are very similar, and this will be also translated into a random walk across this graph. This random walk across this graph, we can just construct the transition probability matrix, and from the transition probability matrix to spectral decomposition to obtain eigenvalues and eigenvectors. If we take a small subset of these eigenvalues and eigenvectors, we can reconstruct our data points with a linear combination of them, and then maintain certain important properties, like invariance of the distances. The second method is the local linear embedding. The first part of the local linear embedding is to identify for each data point its neighbors. It could be, for example, with the algorithm of k neighbors, which just takes k of the closest data points for each point, xi, for example. And then we would like to create a linear combination with certain weights, wij, which relates all the data points with respect to the data point we want to reconstruct. We can just construct the error function, which tries to punish bad reconstructions of the initial data point xi with respect to this linear combination. Afterwards, we'd like to use these weights for a reconstruction in a lower dimensional space with vectors y1, y2, y3, until the dimension of the new space. And in this new space, we would also like to solve the least square problems, where we will be checking the new embedding of our data point with respect to the linear combination of the other vectors with respect also to the weights. So in the end, this process would be first to optimize these weights and then afterwards optimize the coordinates of the new smaller dimensional space. The isomap method first relies on the identification again of the neighbors of the data point xi. There can be two methods, either epsilon ball or k neighbors. K neighbors has already been described, and the epsilon ball is very simple. It just means that data points are neighbors if they are inside of a ball of radius epsilon, of the center at the data point xi. In this neighbor relationship, we can construct neighbor graph, in which each entry is either the distance between data point xi and xj, or it's zero if they are not neighbors. We can then calculate for each pair of data points the shortest path to the graph, where we are taking also the points that are not neighbors as a distance that is infinity. Then we can, from this shortest path graph, D, make a spectral decomposition to obtain the eigenvalues and eigenvectors, and once again make a reconstruction in a smaller dimensional space of our data points. Next method is Laplacian eigenmaps, which is also similar to these ones. This method, what is done is first identify the neighbors with either epsilon ball or k neighbors method. And from the neighbors matrix, instead of using the distance function that we used previously, we use a special one. It's based on diffusion equations, and it relates each data point with this formula, where T is considered to be the temperature in the diffusion equation. Or we can also use the simple method, where only data points that are really close together are deemed to be having a distance of 1. Then from this matrix of neighbors, we will just calculate the Laplacian, which is calculated first by the degree matrix. And the degree matrix is just each of the diagonal elements, we will be having the sum of the column values. And then from this Laplacian, we just apply once again the spectral decomposition to obtain the eigenvalues and eigenvectors, produce a representation in lower dimensional space. Next method is the dimensionality reduction by learning an invariant mapping. And it is based on similar ideas as the previous ones. First, we define a matrix which has a value of 1 if 2 points are similar, or has a value of 0 if 2 points are not similar. In this case, we can consider that similar points are close points. Like, for example, xi is close to xj, so ij is 1, xi is close to xk, so it's not close to xk. So these points are not similar. Each of these data points then can be transformed via mapping. It has certain weights w to a lower dimensional space. And these weights can be optimized with this loss function. This loss function is based on the intuition of having a mass model with springs, in which we will be having for each data point a spring that's connecting all the other points. Points are similar are going to be attracted, while points that are not similar are going to be repelled. Finally, the autoencoding variational bias is a method that is based on the basic assumption that each data point is produced by a hidden process, hidden random process that involves latent variables. So the process to generate a data point is first, we will be sampling a latent value from the latent space Z. From this latent space Z, we'll just be taking out with a random procedure with parameters theta star, which are unknown, a value of x. This is the basic assumption on how the data is produced. And how does this method work? This method works in the idea that we will be wanting to approximate to the distributions that both generated the data and also the distribution that tells us how the latent variables were producing the data. So we'll be using two distributions. A decoder, which takes each value of z and then gives a probability distribution on the space x, and the encoder, which on the other hand takes a data point and tries to identify which are the latent variables that most likely produce the data point x. These probability distributions can, for instance, be normal distributions which have certain parameters mu or sigma. We would like to be optimizing these parameters mu sigma to get the best distribution. So in the end, the objective is to be able to approximate to the probability of having a certain data point with respect to these parameters. The problem with this integral is that it is in general intractable. So to go around this problem, we will be using the encoder and decoder to maximize the log likelihood of this marginal distribution by means of the variational lower bound. We will be talking about this a little bit more in later sections after we make the comparison of all the methods that we have already described. This table summarizes all the characteristics of the already described methods, and from this table we wanted to find out which is the best model that can be used for our problem. So if we recall what's our problem is that we will have images and we want to embed them into a lower dimensional space. And it would be ideal, for example, that we can also encode the process that has produced the data. Because of this, we have chosen both autoencoding variational bias and the dimensionality reduction by learning and invariant mapping. Why did we choose the autoencoding variational bias? We chose it because it is trying to do latent variable separation. So it goes deep into the real process that has produced each of our data points. In our case, for example, images. So imagine the setting in which we have an image and we just want to identify the latent variable that has produced it. And in the best case, this latent variable will be represented by the true position at which each image was taken. So latent variable would be the geometric space. On the other hand, the dimensionality reduction by learning and invariant mapping algorithm is very interesting because it learns a model that can later on add and translate into smaller dimension new data points. Some of the other models are not just do the and just take a fixed number of data points and transform them, and then later on new data points have to be further processed to get the new representation. But in this presentation, I will be mostly focusing on the autoencoding variational bias because we have done some work on it. So the autoencoding variational bias, one of the questions that might arise from this method is what happens with this objective function that we're trying to maximize. So we recall from the previous slides, what we're trying to do is to approximate the marginal distribution of our data set with respect to the parameters theta. To do so, we are going to maximize what we call this lower variational lower bound, but the variational lower bound, and this maximization is with two dependent parts. One of the parts tries to make the distribution of theta of x to be really close for the data points in our data set. That means that it's trying to overfit distribution so that it's very likely to see the data points. On the other hand, the right part of the equation on the right hand side, what it does, it's trying to map our distribution Q of the encoder, but it's most likely to be really similar to the posterior distribution. So we have two forces that are competing against each other. So one question is, what happens if we can, for example, find a new lower bound, but this is parametrical, and it depends on a parameter alpha and beta that tries to balance each of these two forces. We just substitute what is the actual value of the Kullback-Leibler divergence, then we get this expected value. From this expected value, then we can just introduce it into the the equation to obtain the certain relationship. This relationship is very interesting because we would like to be testing what happens if alpha is different than beta. Can we still efficiently optimize this new lower variational bound? And the answer is that not quite, because, well, the last term can still be approximated with the Monte Carlo method, and the middle part can be also approximated either with Monte Carlo or analytical, depending on our choice of the distribution that we'll be using. This was already done in the normal article, but the first part is still intractable because it's the objective that we want to be approximated, and approximated to this function is just an intractable problem. So in this sense, one of the questions that have arisen and we tried to tackle was if new method could be already obtained that was also balancing these two forces, but the result was that it was not quite possible to have this new method that balances both forces. So in that sense, this theoretical result could not be obtained. Now, a new question might arise from this one, and it's to extend this method, which was already extended in the article, but go a little bit further into the variational inference. And what does variational inference talk about? It's just assuming that our parameters, the ones that are generating our data function, our data, are also random variables. What happens when this does? Can we also then estimate some distributions on the data, depend on the parameters that we are using, and also on the latent variables? So this is the next research question that we'll be tackling, and the next direction. Still, there are not results because we just focused in the second part of the seminar to obtain a method that is appropriate enough for the dimensionality reduction, and then we just started working on the theoretical questions that we can address for this project. Then afterwards, what we can do when we have already worked and implemented, for instance, the autoencoding variational bias, is to test it with, for example, a dataset before using the robot images. The North dataset is a set that is comprised of stereo images pairs of 50 uniform color toys under 36 azimuths, 9 elevations, and 6 lining conditions. Now, these images that you can see here are already from the article that talks about the dimensionality reduction by learning an invariant mapping. And why are we choosing this dataset? Because in this sense, it also tries to capture certain information on the location and orientation at which the objects were taken. And also, it's easier if we first start with a toy example problem before we take the actual data set of the recordings of the small robot. So this will be serving for our purposes later on. So what are the results that we have obtained? What we have obtained is a wide range of dimensionality reduction methods that we have analyzed. So we could analyze why each method was better than the other ones, and why we have made the certain decisions about the choices. After that, we chose the autoencoding variational bias because of its explanatory abilities of the latent variable set that produce the data. Then later on, we tried to address some theoretical questions on the autoencoding variational bias and assess the feasibility of a new type of optimization via parametric lower variational bounds. Although this parametric lower variational bound was not able to provide a new optimization, still it was an interesting question to be addressed. So the conclusions for this seminar is that in the seminar we could already make a preliminary study of what was done to establish some research basis for the actual project later on. We also revised a lot of dimensionality reduction methods to choose for the embedding of the video recordings, which is the key element of the whole project. Later on, we also started tackling the problem of working with the autoencoding variational bias article because it's a really involved method, and it was studied in more detail to get more insights. And finally, a clear outline for the master project was traced, and it's described as follows. First, we will do a theoretical analysis of the chosen methods that we've already done. like the autoencoding variational bias, then implement the dimensionality reduction method and test it with a toy dataset, for example, the North dataset. Then apply the dimensionality reduction to the video recordings from the robot. So that's already testing with the field problem. And finally, from the embeddings, reconstruct the orientation vector that has truly produced each of the data points. So with this workflow, I will want to finish my presentation, and thank you everybody for attention. Now I just need to stop this.